Hi everyone. If you're studying A-level physics, you will know that the longer response questions can be really tough. Do you ever feel like you understand the concept but just cannot translate it into a top grade answer? Or maybe you lose marks because you're not quite sure what the examiner is actually looking for. In this tutorial, we're going to demystify these difficult questions, focusing on the topic of forces. We'll break down exactly how to approach them. I'll share my top tips for structuring your answers and walk you through some worked examples step by step. By the end of the video, hopefully you'll feel much more confident in your ability to ace those longer response questions. Enjoy the video. Right, the thorny issue of longer response questions. So what we tend to find is that some students can understand the physics really well and answer calculations very well, but then they lose a lot of marks on the longer response questions. So there's some general guidance here which we can go through, and then we're going to look at some specific examples, fairly straightforward and then getting more difficult. So there's a few of these things you will have heard before. So read the question, it's so important. Read it again, read it several times, make sure you understand it. Get a pen, underline the key words in the question or the key information. Why have they given you this information? Look at the number of marks. Generally it's going to be 5 or 6 marks. That means you need to be writing at least 5 or 6 points, generally speaking. Maybe not a brief, maybe not a draft answer, but just a few bullet points. What you're going to include either in the margin or on a piece of scrap paper, just to give you an idea before you commit to writing. The bullet points thing's a lot of discussion about this. I think most exam boards will be fine with those, but probably just check with your teacher and with the exam board, because normally it should be fine, but sometimes some exam boards can be a bit fussy. Terminology we'll talk about in a moment. Generally speaking, you have to demonstrate and use good terminology. Clarity is very important, and we'll talk more about this later on. So if you say it accelerates, or start a sentence with because it's heavy, then that's a little bit vague. So clarity is very important. And once you've written your answer, read through it in your head and not out loud in the exam. Does it make sense? And if you can make any changes at that stage, then that would be a good idea. So the command words, we don't need to spend too long on this because this is more related to humanities and essay writing. But these words mostly are used in the physics exam. So define is very specific. Describe is a bit more detailed but doesn't involve any understanding. Explain is obviously more complex. Justify and discuss mean taking in, thinking about supporting arguments or maybe other points of view. And then evaluate, again, that's more of a kind of, it's got a humanities connotation, but you might be asked to evaluate the validity of a statement or of maybe a student's concept. So we go from low marks and low complexity and increasing from maybe 1 or 2 marks up to the 5 or 6 marks. So you won't be asked to write out the meaning of the key words, but you do need to recognize if you see define and describe, that's probably 1, 2, 3 marks. If you see discuss, evaluate, that's going to be more marks. Right, this is your entry-level question at A-level. You will have seen this at GCSE probably, and it might have been for 3 or 4 marks, possibly 6 marks. You might get a question like this at Physics A-level, but probably it's going to be more difficult, or it'll be a slight variation on this. But I think it's a really good starting point. So we've got describe and explain. That's 2 separate things. So what happens and why in terms of the motion. And we've also got to look at the context or the limit. So from the moment they jump out of a plane until they reach terminal velocity. Very often students write about then the parachute opens and so on. You won't get any marks for that at all. So you've really got to read the question and think, what are they asking in particular? So we're going to look at stage by stage, diagrammatically, and then we're going to look, pull it all together and look at a model answer. So right at the start, time is 0. The only force acting is the weight. There is no air resistance. So here we've got the maximum resultant force. So the acceleration is as big as it can possibly be which is equal to g, which is 9.81. Now already that's a counterintuitive idea. Maximum acceleration with zero velocity. It sounds back to front, but that's absolutely what happens. A few seconds later, the speed has increased, so now the air resistance will exist, but it won't be that big. So we're not moving at terminal velocity just yet. So the length of these arrows is very important. The weight doesn't change, but now we have a drag or an air resistance acting upwards, opposing the weight. So now we have a resultant force lower than we have at the start. W minus R is smaller than W. So the acceleration is not zero, but it's going to be less than g, less than 9.81. So this again is a really important idea. The acceleration has got smaller because we got faster. Bigger speed, bigger drag, reduced acceleration. Very important, quite counterintuitive. Okay, so 15 seconds or thereabouts has passed. We've now reached the terminal velocity. Many students remember this from GCSE and go straight to this in their answer and miss out the previous points, therefore limiting the marks you can get. So at this point, the forces are balanced. We're moving so quickly, 150, 180 miles an hour, maybe faster than that. The air resistance is so big, it's as large as the weight. So we could make reference to Newton's first law here. We're now moving at constant velocity. Our acceleration is zero. Very important, that does not mean we stop moving. It means we've stopped accelerating. Balanced forces, resultant force is zero, acceleration is zero. Then we could talk about the parachute opening, even though that wasn't in the question. So we may as well do the full journey. So now we open the parachute, we're going at 200 miles an hour at enormous surface area, a huge force upwards. So now the force upwards is bigger than the weight. That does not mean we move upwards. That's a really common misunderstanding and totally incorrect. We are still falling, but now we are decelerating. So our acceleration is now less than zero. And then we could talk about the final terminal velocity, or the final stage before we land. So we now reduce our velocity, so the drag, the air resistance reduces as we slow down until the weight and the air resistance are the same size. Once again, the forces are balanced, therefore zero resultant force and zero acceleration. Okay, so we did a few extra bits there. The last two stages we didn't need, just for completeness. So the model answer would be this. So we've also got here some really important terms or tools called connectives. Now again, you don't need to know this term, but you do need to be able to use these words. So initially, eventually, because, therefore, this is shown by, at this point, this is because of. These link your answer together. So it's not just about getting the right physics, it's about getting the right physics in the right order and making it all connect together, hence connectives. So we need to say that the starting word is really useful. So you could say at time equals zero, or initially, or at the start. And what we're doing effectively is telling a story. So right at the start, the only force is weight, therefore we have maximum acceleration g. As the speed increases, the air resistance, the drag increases. So that's really important. The faster we go, the bigger the drag. This means that, or this means, that's another connective, the resultant force down is reduced. Really important. So now W minus R is a smaller value than just W on its own. So, that's another connective, the acceleration will be less than 9.81, or it is reduced. And we could make reference to Newton's second law, F equals ma. Eventually, that's a really nice connective, or you could say after some time, but eventually just keeps it open. The drag force equals the weight. At this point, the resultant force is zero, or the forces are balanced, but the resultant force is zero is a good phrase. So the acceleration is zero, and then we call this terminal velocity. So we've got 1, 2, 3, 4, 5, 6, 7. So for a 6-mark question, you would need 6 of these points. So it's a lot of detail here, a lot of terminology, a lot of clarity, and we're telling a story right at the start until what happens at the end. Example number 2. So I've included this one because it's very similar to the first one, but it's more difficult, partly because of the context, but also because it's quite similar to the first one. We've got an object moving through a fluid. but it's not quite the opposite, but it's a little bit similar and a little bit different. So it's a really useful one to consider. So let's read through it. So a steel ball, we've got an object here, is released from rest. So that's our t equals 0 there. Actually not t equals 0 on the graph, importantly, but in the experiment. And it hits the liquid, so it's accelerated, and then it's going to slow down. In fact, sorry, that is t equals 0. There we go. So the ball descends vertically in the air in the liquid until it reaches the bottom of the cylinder. Okay. The graph now shows how the velocity of the ball changed after it was released. Describe and explain. Once again, really, really common words, command words. So what is happening and why is it happening? But specifically looking at the acceleration. So we could mention the forces and resultant forces, but specifically what we're interested in the acceleration. From the point after it entered the liquid, right, so this is important. So even though this is t equals 0, and we've got this acceleration, we're only interested in from this point here until it reaches the bottom of the cylinder. 6 marks. Okay, so lots and lots of stuff going on there. What I'll do before going through the model answer, I just want to consider a very typical student answer. So a lot of my students have written this kind of thing in the past. So as the ball enters the liquid, it continues to accelerate, but at a slower rate because of the resistance of the liquid. The drag force increases as the ball goes faster. Eventually, the drag force becomes equal to the weight of the ball, so the forces are balanced. Constant speed, acceleration is 0. Right, at first reading, that seems quite good, but there's not enough detail, certainly, and there's one or two fundamental misunderstandings. So let's have a look. It continues to accelerate. Well, it does, but we need to talk about the size of the acceleration. So the gradient of this line here is changing. Initially, the gradient is quite large, and the gradient gets smaller. So really, we need to make reference to the VT graph. Initially, we have a large acceleration, and then it reduces. A slower rate is problematic. Slower is to do with speed. Well, it is slowing down, but then we're talking about acceleration. And if you talk about the rate of acceleration, that doesn't really mean what we want it to mean. The rate of change of velocity is acceleration. So I wouldn't use the word rate when talking about acceleration. But the resistance of the liquid, yeah, so it's slowing down possibly due to the increase or due to the resistance. The drag force increases as the ball goes faster. Right, that's fundamentally wrong. The ball is slowing down. So what they've done here is they're thinking about the person jumping out of the plane and the terminal velocity when the speed increases and the drag increases. This is the other way around. The drag is causing the velocity to reduce, and as it gets slower, the drag also reduces. So that's fundamentally not right. Eventually, good connective, the drag force becomes equal to the weight of the ball. Well, that's true. So the forces are balanced. Then it moves at constant speed, acceleration is 0. So it's quite good. There's some good physics in there. Not enough detail, as we'll see, but also we've got this fundamental misunderstanding here. That's totally incorrect. So definitely limited to 4, possibly only as many as 3 marks. Right, so the best answer, let's go through this one. Before we do that, let's go back to this idea of weight and drag. What's happening? So the weight in each of these scenarios doesn't change. So we're talking about right at this point here, the point where we enter the liquid. We're moving very, very quickly. We've gone from air, where the drag was relatively small, into a presumably viscous fluid, so we have a large drag. The drag is larger than the weight. That causes a deceleration, which is why we're slowing down. And because we've got a large resultant force acting upwards, then we have a large deceleration. That's a steep gradient. As the ball slows down, then the drag reduces. So maybe kind of round about here, we've got a reduced drag. It's still bigger than the weight though. So we still have a resultant force acting upwards, therefore deceleration. We still have a deceleration, but it's a lower deceleration than before. It's less steep. Until eventually, when we have our terminal velocity, the ball has slowed down so much and the drag has reduced, so now it's the same size as the weight. So there we have our balanced forces and 0 acceleration. So here we go. Model answer. Initially, telling the story, the resistive force or drag is greater than the weight of the ball. So there is a resultant force upwards, not downwards, as we saw in the first example. which causes the ball to decelerate. So we've got deceleration. So we're answering the question, what happens to the acceleration? The resistive force decreases as the speed decreases. This is a really important point. Very often students go straight to this final balanced forces scenario and they miss out these middle sections or the earlier sections, and therefore limit the marks. So the resultant force decreases and the deceleration decreases. And we could make reference to Newton's second law, F equals ma. And then once again, lovely connected, eventually the resistive force is equal to the weight and the resultant force is 0 and the acceleration is 0. So again, we've told a story, we've got the right terminology, we've answered the question from the right point. So a lot of students would talk about this first section here. No marks for that because we only need to talk about it from the point where the ball enters the fluid. We've got clarity in our answers. We've made reference to formula, and we've got 1, 2, 3, 4, 5, 6. Yeah, this would be a solid 6 marks. Right, so do give this some thought. Do look at lots of other examples. Longer response questions tends to be where a lot of students, even really good students, lose marks. And it's very, very difficult to get 6 marks on these longer response questions. So lots and lots of practice. Write out these answers again and again. Maybe work with someone else and exchange your answers and critique each other's answers. You can also look at ChatGPT or equivalent to give you model answers or good or bad answers for different questions, and that's quite a useful activity. Okay, so what's next? There are lots more videos on YouTube. If you're still focusing on forces and dynamics mechanics, then you might want to look at the next video in the playlist, which is Physics A-Level Vectors. Alternatively, you might want to go to payhip.com, Grade A Physics. The link should be in the description. And here you've got lots of structured tutorials, practice questions with work solutions, quizzes to check your understanding, exam questions with work solutions, and progress tracking. So see you soon in the next video or on PayHip. Bye.